Hello guys, welcome to this tutorial. In this tutorial, we're going to change the memory address where we load our second bootloader to, and then we're going to check if the PCI bus is installed and also if the CPUID instruction is available to us. So, let's start. As you see here, I have changed the memory address where we load our second bootloader to be 7000. Why is that? Because, as we see here in this real mode address space representation, the first and only megabyte that we can use in real mode, we see that this address here gives us 480 kilobytes of conventional memory, which makes it a very good place to put our second bootloader to. So, we load it basically there, as we said. I explained the math here. Basically, we have the segment and the offset. We multiply the segment by decimal 16 and we add the offset. The segment is 0, this is 0, and we have the offset left, 7000, and we jump to it. We set our origin to 0x7000, and we set the data segment, the extra segment, and the stack segment to 0. We set our stack pointer to 0x7c00. Why? The stack, as we know, grows downwards. Basically, this value, 7c00, will grow downwards. This value will become less and less until it reaches 0. It will not really, reach 0, of course, but it will grow downwards. This will give us almost 30 kilobytes of memory. If we check our address space here, we have 0x7c00 where our first boot sector is loaded. But we will not touch our first boot sector because we're going to go towards 0. That's it. This will give us 29.75 kilobytes of conventional memory. Here I do the math, and you can see it. We have the stack segment is 0, our stack pointer is 7c00, we multiply it by 16, it's 0, and we have 0x7c00 left. If we make it into decimal, it's 31,744. We divide it by 1024, and we have 31 kilobytes of memory space that we can use. Also, the address where we load the memory entries, the number of the memory entries, we set it to 0x500. Again, a good value that we can use for conventional memory. So, that's it about the memory. Let's speak about the PCI bus check and the CPUID check. So, I have created basically a do checks label, and here we call the check PCI bus and the CPUID check. For the PCI bus, we're going to use this BIOS interrupt 1A with B101 in the AX register. This, if the PCI bus is correctly installed, it will give us the carry flag clear. And of course, the AH will be 0. So, what we do here, basically, we save our state. We save all the general purpose registers. When we finish, we restore it. We show a message, and we move into AX0xB101, and we use BIOS interrupt 1A. If the carry flag is set, we jump to the error message. Otherwise, our PCI bus is installed correctly. Then, what about the CPUID? The CPUID, as we can see here, gives us a lot of information about our CPU. Its vendor string, model number, and most important, the CPU features that are supported. The code is quite simple, and I will try to explain. First of all, we need to know which are the EFLAGS. The flags are here. The carry flag, the parity flag, the auxiliary flag, the zero flag. Basically, we care for this one. The 21st bit, which shows us if we can use the CPUID instruction or not. So, how does the code work? We save the EFLAGS 2 times, these 21 bits. Then we XOR. If you need help with the XOR operation, I can make a video about all the bitwise operations. So we XOR what we have in our stack pointer with this value. This value, if we make it into binary, we see that the 21st bit is set into 1. So we XOR what we have in the stack pointer with this. And then we load the changed EFLAGS. And then we push them again to the stack. We save them again, basically. Then we pop them into the EAX register. The ID bit might be changed and might not. We'll check it soon. Now we XOR what we have in the EAX with what's in our stack pointer. Basically, in the EAX, we're going to store whichever bits were changed with the XOR operation. And then we restore the original EFLAGS. Now, we use a bitwise AND operation with the EAX and this value that we used above. If EAX is 0, means that we cannot use the CPUID instruction. If it's not 0, means that we can use it. So here, basically, it is the same code exactly. The only thing that I did extra is I saved the general purpose registers. It's a good practice when you use a function just to be safe. And when we finish, we restore them. Then we do the exact same code as in the OS dev article. And basically, let's test our code. We clean, we make, and we use Kemu. So, yes, I also created the menu. I will show you. We can see our memory map, and we can also do some checks. And we see that the PCI status, that the PCI exists, and the CPUID instruction is available. In the next video, which I hope is going to be next week, we are going to use the CPUID instruction to get a lot of information about our CPU. And then we'll start the process of entering into protected mode. So, yes, I need to show you the menu. Basically, it's just a menu string here that we use when every time we ask the user for input. Basically, here, every time we ask the user for input, we show this menu string. That's it. So, thank you very much. If you have any questions or something else that you would like to see, just write it in the comments. I will always answer and I will be very happy to answer. If you liked the video, please like and subscribe, and I'm looking forward to making the next one. Thank you very much.